Stars much more massive than the Sun, 2, 3, 5, 10, even 20 times the mass of the Sun, have short, violent lives. Because of the large gravity, their cores raise to very high temperatures, enabling fusion to occur all the way up to iron in the periodic table. They end in spectacular detonations called supernovae and leave behind bizarre compact objects, neutron stars and black holes. Stars more massive than the Sun are able to ascend the fusion chain. They are massive enough to create ever higher temperatures, pressures, and densities, such that fusion can occur between more massive nuclei with larger positive charges. Fusion proceeds in stages. For example, a helium nucleus can fuse with carbon to make oxygen, another helium nucleus can be added to make neon, and yet another to make magnesium. And these fusions can occur in different combinations as well. Notice that because helium is the second most abundant element, fusion can occur increasing the atomic number by 1, such as when a hydrogen nucleus or a single proton is added, but also by addition of 2 protons in a helium nucleus. That's what gives the sawtooth pattern in the periodic table abundance curve. It's caused by the fact that most of the fusion is of units of 1 or 2, and the extra amount of additions of 2 means that even atomic numbers are slightly more abundant than odd atomic numbers in the periodic table. In the Sun, at a low degree, and in other stars more massive than the Sun at a higher degree, there's a second fusion process that creates helium from hydrogen, called the Cno cycle. In this case, carbon, nitrogen, and oxygen, already present from pre-primordial material as the star formed, catalyze the reactions that lead hydrogen to helium. This second energy process is more complicated, but it contributes significantly to the creation of helium in low-mass stars. The most advanced nuclear reactions to create the heaviest stable elements require phenomenal temperatures. For example, oxygen could combine with carbon to make silicon, and oxygen could combine with itself to make sulfur, and 2 silicon nuclei combine to make iron. This requires temperature of billions of kelvins, perhaps 5 or 10 kelvins to get up to the iron. Only the very highest mass stars, which are intrinsically rare, can create high enough core temperatures for the heaviest stable elements to form. The result of this sequential evolution in a high-mass star is an extraordinary physical situation where the star has an onion skin structure. It's not quite as pristine as the simple cartoon form because there's some mixing between the layers. But basically, moving outwards, we still have unfused hydrogen in the very center, followed by helium, followed by the heavier elements, carbon, and so on, up the periodic table until the very hottest center part of the Sun contains an iron core. This is an extraordinary form of iron in a high-mass evolved star. It's denser than water, it has a temperature of billions of Kelvin, and yet it's a gas, a plasma. I said the heaviest stable elements because the fusion process only works to get you up to iron. In the binding energy per nucleon curve, there's a stability trough at iron. And this means that in nature, you can get energy out of fusion in going towards iron from lighter elements, but you can get energy out from the fission of heavier nuclei moving towards iron. Iron is the most stable element. What this means in terms of a star's life is iron is the endpoint. No more free energy is available by fusing beyond iron, so it creates a logjam, or a slag heap at the center of the star, ending in iron. Extra energy is required to go beyond iron. Summarizing the stages of evolution of an extreme star like a 25 solar mass star, we see that these different fusion stages involve a crescendo of timescales. The carbon fusion of the massive star takes only 600 years, the neon burning just a year, silicon forms in a day, and the final collapse state of the star takes less than a second. In the blast wave that moves out at relativistic speeds from the collapsed star, elements are synthesized all the way up to the transuranic elements at the top of the periodic table, in temperatures that instantaneously reach 10 billion Kelvin. With this piece of the story added, for high-mass stars producing heavy elements, we've explained most of the characteristics of the periodic table chemical abundance. The sawtooth pattern, the fact that there's a third peak at iron, the most stable element, and the subsequent fall-off because of the difficulty of creating even heavier elements requiring such high temperatures. Summarizing cosmic chemistry, we have primordial hydrogen and helium, the most abundant elements in the universe, with everything else taken together just a trace element. We have carbon, nitrogen, and oxygen, the carbon produced in relatively low-mass stars, and these are the life elements present at a few parts in 1,000 relative to hydrogen and helium. We have the creation of the elements up to iron in massive stars, in a flurry of activity at very high temperatures, and then we have elements beyond iron produced in supernova explosions, but also in a slow manner. In practice, there are two methods for creating heavy elements called the R and the S process. The R process, or rapid, occurs in supernovae, while the slow process is the gradual diffusion of neutrons into an atomic nucleus to increase its atomic number by 1, and this can occur in the envelopes and cores of massive stars. The final features we can explain are the sawtooth pattern caused by the addition of helium nuclei in the fusion as well as hydrogen nuclei, and then the deep trough at the light elements caused by the unstable beryllium nucleus, representing a bottleneck which leads to the low abundance of carbon relative to hydrogen and helium. Perhaps the final insight in cosmic chemistry is that we have an erroneous way of thinking of stars. It's inevitable to think of them as light bulbs in the sky. But that's not actually what's going on, because we know that the efficiency of mass-energy conversion is actually quite low, less than 1%. We should instead think of the stars as chemical factories. It's as if you had a car factory somewhere in Michigan and you flew over it at night. You might see light leaking out from the windows. If you had an infrared camera, you'd see heat leaking out as well. And you might imagine that the factory was really making heat and light. Of course it isn't. The factory is making cars. That's what it's built for. Stars are making heavy elements by fusion, and the light we see from them is simply a byproduct. In that sense, stars are chemical factories, and since they make the biogenic elements, the universe is built for life. Since this process has been going on for over 13 billion years since the Big Bang and the first stars that formed, the universe has steadily been increasing in its abundance of cosmic elements beyond hydrogen and helium, and becoming more ripe for life. Stars do naturally what alchemists have only dreamt of, making heavy elements, including lead and including gold. Low-mass stars can make carbon, the biogenic element and essential for life. Higher-mass stars make heavier elements, and these elements are produced into an onion skin layer where the highest densities and highest temperatures can create the heaviest elements, up to iron, the most stable element. Energy is needed to go beyond iron, and often this occurs in a supernova explosion. The titanic blast wave resulting from the death of a massive star can forge the heaviest elements up to uranium instantaneously at temperatures of billions of degrees. This process, cosmic nucleosynthesis, has been going on for 13 billion years since the first stars formed in the infant universe.